Welcome to this video. We are going to work through some problems in our honors physics notes. We're starting on page 11, number 7. An outboard motor for a boat is rated at 35 horsepower. Horsepower is another unit for power, and they give us the conversion to watts here. If the motor can move a particular boat at a steady speed of 35 kilometers per hour, then what's the total force resisting the motion of the boat? Now, if the speed is constant, then here's what we have. You've got the boat like this. The motor is providing this forward force, propelling the entire boat forward. But of course, there is a resistive force. You know, maybe it's air resistance, maybe it's the water, but there's some resistive force pushing back like this. And here's the captain leaning forward. Okay. So, captain, what's the captain's hat look like? Clearly, I don't know. So now, if the speed is constant, steady speed, then this resistive force of friction, I'll just call it, has to balance this forward force from the motor. Horsepower, 35. Let's go ahead and convert. We need to get rid of the horsepower, so we need HP over HP to cancel it out. Of course, we'll be moving it into watts, but now we need to add some values here and here so that the conversion factor or conversion fraction is just equal to 1. So we add the values provided. 1 horsepower is equal to 745.7 watts. We can do that calculation times 745.7. And I'm not really going to write that down. Let me just put 26 kilowatts, although I know that really I have to keep those extra decimal places. This is just shorthand. So it asks for the total force, total resistive force. Now, if we look at the equation for power, the one with speed, since we've been given speed, the boat is moving forward. The applied force from the motor is forward, so the angle is 0, and cosine of 0 is all just 1. So I'm going to drop that. Okay, so now the equation is this. We're applying the equation to the motor, its power, and the motor, its force. We already know that the force of the motor will be equal to the friction force, and this is ultimately the unknown. So all we have to do then is plug this in, plug that in, calculate the force of the motor, and that is our answer for the friction force, because they're equal. The only trick then is, okay, so we've got our 26099.5 watts. A watt is a joule per second. We need in force, we need newtons, but we're going to need meters per second for the speed. And so we convert 35 kilometers per hour. 1 hour is 60 times 60 seconds. So now I've canceled out the hours. Kilo, we need to cancel that so that it's in meters per second. And you put the equal power of 10 on the other side. So the kilo cancels. And what is our speed? We do 35 over 3600 times 10 to the 3. 9.72. And that is our speed in meters per second. When you solve for force, right, divide both sides by 9.722. Let's do this. And then just divide by the 9.72222. There's our answer, 2 sig figs, 2,700 newtons. Now that's what we calculated for the motor, how much force the motor must exert to achieve this power at this speed. But that force from the motor is equal to the force of friction, so that's our final answer. On to the next one. So number 13, there is a piece of information missing. it's supposed to say an acceleration of 0.30 meters per second squared. So here's what's happening. You've got an elevator. There is some giant metal cable that's like wrapping around a huge spindle or motor. And okay, so now the elevator feels a downward force from gravity, but an upward force from the cable. That is literally a tension force. However, I've drawn the arrows incorrectly. If it's accelerating upwards, then there must be a net force upwards. To get an upward net force, tension has to be bigger than mg. So let me try my tension arrow once more. There's the gravity force, a little bit longer. There's the force of tension, capital T. Now I know that net force from my diagram, as soon as you draw a diagram, right? Most of the time, the reason we draw a diagram is so that we can write an expression for net force. And so now I have tension plus mg, except hang on, I have to make mg negative because it's down, and that ends up subtracting mg from tension. That makes sense. Mg cancels some of the tension, and the net force is just the amount that does not cancel. The black arrow there would be the net force. Oops. Okay. All right then. So can I find anything from this equation? Well, not quite, because I don't know F net, and I also don't know the tension force. But Newton's second law says, hey, that net force right there is equal to mass times acceleration. So let's use Newton's second law to substitute in right here. Now I look at this equation and I say, I know mass, 265. I know acceleration, 0.3. G is 9.81. Let's find tension. I will add mg to both sides. And tension is going to come to, I'm going to have this plus mg. So that's going to be 265. And watch me be fancy. I factored out the mass. And I did, I moved this over. I factored the mass out from both terms, and I added a plus g. You don't have to do it this way, but it's fun to see those tricks. So that's going to be 10.11, yeah? 3 added to this place. That gives me 11, a 1, and the extra 1 carries over to give me 10. 2679.15. Maybe that'll be useful. I don't think I actually... okay, no, I didn't even read the question. I do this all the time. I forget to read the question. A says, determine the tension in the cable, and we just did that. We would round this for siggy figgies. That's 3 sig figs, 3 sig figs. Ooh, just 2 sig figs there. So my tension would be 2700 newtons. Part B, find the net work done on the load. That would be like the elevator. I guess they didn't even say elevator. I see cable and vertical lifting, and I think immediately my mind goes to an elevator. All right, the network uses the net force. Now, the net force we said earlier was upwards, because it's how much of the tension doesn't cancel after you take away gravity from T. So F net is up. The thing is moving up. So what's the angle from the force net to the distance? 0. And in that case, cosine of 0 is all just 1. Okay, do I know net force? Yeah, we know net force. It's m times a. And the upward distance is 18. So you can plug in 265 times the 0.3 times 18, and you get your answer. $14.31. And with Sigger figures, it's 1400. Joules. Work is in joules, just like energy. Part C. We are going to run out of room. That's okay. Find the work done by the cable. Okay, so work is force times distance times the cosine of the angle. Again, cable pulls up. Distance is directed upward. So the cosine of 0 is what we need. You plug in the force of tension, that's this value. You plug in the 18 meters, that's given right there, 18, and you solve the equation. Okay, we're not going to worry about that. For part D, what's this? Part D says the work done by gravity. Yes, same kind of process. Instead of the force of the tension, you put the force of gravity to get the work by gravity. And in this case, the force of gravity is just the mass, 265 times 9.81. The distance is the same always for all of the different forces you might consider. It never travels a different distance because it's only moving once, and all of those different forces act while it moves 18 meters. And this time, for gravity, gravity pulls down, the distance is up, so the angle from that to that is 180. This would be cosine 180. And we know, of course, cosine 180 is -1. That's part D. You plug it in and solve. Part E, the final speed. Yes, yes, yes. Okay, so part E. Instead of doing like, there are these equations, AT, or maybe you'd think about the one that has distance in it, 2a times displacement, but of course the upward displacement in this case is just equal to the distance. But instead of going that route, we're going to use the work kinetic energy theorem because we already found W net in part B. The work kinetic energy theorem says W net is equal to the final kinetic energy, 1/2 mv squared, final, minus the initial kinetic energy, 1/2 mv squared initial. So you plug in your W net was 1400, but use the unrounded value, 1431. The mass was 265. The final speed is what they asked for. And the initial speed was 0, so you have no kinetic energy at the beginning. How do I know the initial speed was 0? Assuming it started from rest. And you solve for VF. I will solve this just because the math might be a little tricky. We want to multiply both sides by 2. That cancels out the 1/2. We want to divide both sides by 265. That cancels out the 265. And so on the right side, what I'm left with at this point is VF squared. To get rid of the squared, we square root both sides. Okay, square root of 2 times our answer, second answer, over 265. 3.3 meters per second. That's a little fast for an elevator. Maybe it's not an elevator. Anyway. Okay, what's next? Let's do number 1 on potential energy. This is page 15. A 1.6 meter tall person. Oh, they're lifting a book off the ground. Okay, so that it's 2.2 meters above the ground. Okay, so here they are. Why do I keep drawing their arms like that? Here they are, holding the book. And their height is 1.65. Oh, that's their height. That's the height to their head. The book's height above the ground is 2.2. What is the, okay, and the mass of the book is 1.65 kilograms, and you probably noticed that I got this wrong. This is 1.60, not 1.65. All right. Find the potential energy of the book relative to the ground. So if this is your 0 level, then what is the height of the book up from there? 2.2. So then for part A, the potential energy, gravitational, is mgh, 1.65 times our 9.81. And the height from the ground, if that's the 0 level, is 2.2. And you get your answer. For part B, find the potential energy relative to the top of their head. So, okay, so here is the top of her head. And now, if this is the 0 level, and you say from that height, how far up is the book, you have to subtract. It's the same mass as before, 1.65 mgh. And this is how you would get the gravitational potential energy relative to the top of their head. Okay, part C. I love part C, but I fear the phrasing may not be super clear. The part C says, how is the work done by the person related to the answers from A and B? Now here is the idea. When they say the work done by the person, what they mean is the person starts with the book right here on their head, and she lifts it all the way up to this final height of 2.2. So how does the work in lifting this up relate to the answers from A and B? Okay, at least that's how I'm going to interpret work done by the person. I don't know, maybe the problem thinks that she's starting and picking it up off the ground, but it's really not clear. So I'm going to say that she's starting by, it's at her head and she lifts it up over her head. So how is that work related to the previous answers? Well, that's pretty straightforward, you know? Work is equal to energy. We haven't really written this down in an equation. I mean, we do have net work is equal to delta KE, but the idea here for part C, in order to increase the potential energy, you have to do work. And in fact, the work needed to raise the book by, what would this be, 0.6 meters? Is equal to the change in potential energy, gravitational, as you raise the book by 0.6 meters. So that change in potential energy is literally the answer we got from part B. We said if you start here and you raise it up, and that's the change in height, how much energy is there resulting from this height difference? That's what part B tells us. And so the answer to C would equal the answer to B. Right? This is in joules, and so is the potential energy. And this is hinting at a fact that we really haven't studied formally, and it's not always, introduced in high school. But here's just really quickly, the work done equaling potential energy, does that make sense? Well, yeah, it does, because if you lift the book up, you have to apply a force against gravity. And you have to apply that force some distance d, which really is the change in your height, or the change in height of the book. And if you push up, right, your force applied is balancing gravity, but you're pushing up. And the height increases, goes up, so the angle is 0. And if we apply the equation for change in potential energy, right, you change your energy because your height has increased. If we look at the left side and the right side, we see, hang on, force of gravity is just m times g. And so in fact, these two sides are equal, left equals right. And yes, the work that you have to do is equal to the change in potential energy. All right, let's move on and take a look at number 9. In number 9, we have a block that is starting at rest, compressed, pushed up against this compressed spring. So right here, let's look at this moment, initial, and then we'll look at this moment, final. We asked the question, does the system have compression, speed, or height? What about at the end? Okay, initially look at the spring. Is it compressed? Yes. How much is it compressed? 0.17 meters, they say. That's the compression. This spring, is it moving? Nope, no speed. The block's not moving. How about height? Well, let's take this height here and make this our 0 level. So anything at this height is 0 meters above the ground, quote unquote, the 0 level. Think of it however you like. So the height is 0 by definition. Okay, at the end, is there any compression? Look at the spring. Is it still pushed down by 0.17 meters? No, it is uncompressed. And so we do not have any compression final. The block has stopped. We ignore kinetic energy of the spring, so that's 0. And yes, there is height, but it's not h. We have to be consistent. This is our 0 level, we said. So measure your height from there. And what is that value? Well, if this is 0.17, and if this is h, then the final height is 0.17 plus h. And so we set up our equation for mechanical energy conservation. We're going to have 1/2 kx squared on the left and mgh on the right. But remember, the final height is 0.17 plus h. And you plug in values. K is, what'd they say? 1800. X is 0.17. We square it. M is 3.5. G is 9.81. And we've got 0.17 plus h. The way I would do this math is I would divide both sides by the product of 3.5 and 9.81. Do the same here. And that's going to get rid of the 3.5 and the 9.81. And then I'll subtract 0.17 from both sides. Let's do that. Okay, so there's the left side. And then I divide by 3.5. I divide also by 9.81. Remember, you can't do a star right here, or else it's going to put that into the numerator, because our calculators will take this, divide it by 3.5, get the answer, and then multiply. We don't want the 9.81 in the numerator. We want it down below, so we do it like this. And then, like I said, now I've got 0.7575 ... equals 0.17 plus h. So I have to subtract the 0.17 from both sides because they are added together. And what does this give us? 0.59 is the final height. Let's put a unit. I checked, 2 sig figs. That's all we wanted. Now, is that the final height? Well, no, it's not the final height according to my 0 level. The final height according to my 0 level is 0.59 plus the 0.17. But they gave me a variable to start out, and so I have to use the variable they've given, but I can still choose my own 0 level and think about it however I like. However, for the h that they defined in the problem, that's the answer. Let's move ahead. Number 12. So we've got a projectile launched into the air at 5.5 meters per second. This is quite exaggerated because the angle is only supposed to be 13.6, which would be pretty low. Okay, and it reaches maximum height. And of course, when it gets there, it is still moving on the x-axis, right? Because it's moving along the x-axis with the same velocity here as the initial x velocity. The x velocity is always the same the whole time it's in the air because gravity only pulls down, it doesn't pull to the right or to the left. Well, in that case, we know Vx. It's just the adjacent component of this right triangle. And so when we do our energy analysis, we say, hey, initial and final. Speed, height, compression. I think I write them in a different order every time. There's no compression because there's no spring or nothing is pushing in or extending. There's no rubber band or anything like that. We do have speed at the beginning, but no height. At the end, we have speed and height because it's still moving and it has it's above the ground. So our equation looks like this. And they want me to know, they want me to figure out what the maximum height h is. But we can plug into this equation. Well, first we can actually divide both sides by mass. Division distributes across addition. So you're going to cancel out this mass and that mass. On the left, m cancels. 5.5 is the initial velocity. The final velocity at the peak is 5.5 cosine 13.6. Because at the peak, your vertical velocity is 0, and the only remaining velocity would be the amount you had at the x-axis, on the x-axis to start out. So you solve that equation. Okay. Subtract this from both sides, then calculate your answer and divide everything by 9.81. Okay. Okay, on to number 13. So this is an interesting one because we're not actually going to solve anything with values. We're just going to utilize the variables given and write some equations, some expressions. Okay, we have a block of mass m attached to the end of a spring. Here's the spring, here's the block. The stiffness of the spring constant, is k. The mass is given initial displacement of x0. So let's pretend that this is the resting position of the spring, and we've moved it over some amount x0. Okay. Maybe I should draw that to where the spring is stretched. Right? We're measuring the spring's displacement. And the initial speed of the mass is v0. So I don't know which way the mass is going, but we're pushing it so that it's got some speed to start out. It actually doesn't matter. You can choose either direction and you'll get the same expression, because with kinetic energy we square speed, right? So that's why the direction doesn't matter. And if the block is going this way, then it moves over and it comes back. And when it reaches the same position, it actually has the same speed again. Okay. Ignore friction and mass of the spring. In terms of the given quantities, use energy conservation to find its maximum speed and its maximum stretch distance. At this moment, right now, the one shown, speed, height, compression. At this moment, it is compressed somewhat. Well, it's stretched, I should say. So it does have potential energy, elastic. It is moving, so it has this, but it's not off the ground. The final moment that you have to pick is, okay, the one when it has maximum speed. If we want speed to be as big as possible, then there can't be any energy wrapped up in potential energy. Like any of the potential energy that existed from the stretch has to have all converted into speed, making speed the biggest possible. So that means now the thing is back at its normal relaxed length. And any of that stretch, any of that elastic potential energy has converted to kinetic. If you do this to solve part A, the equation is 1/2 kx0 squared plus 1/2 mv0 equals 1/2 mv maximum squared. I can multiply both sides by 1/2, divide both sides by m, and the m cancel. I have to divide the entire left side by m, distribute that division to here and to here, and what do we get? Well, this m cancels out, but not for that term because there's no m to cancel. Then I have to square root both sides, like this. And my final expression for maximum speed is the square root of kx initial squared over m plus v0 squared. Yep, there it is. Now, the trick is, I said, okay, to find maximum speed, don't let the energy be wrapped up here or here in compression or height. If you want to find the maximum stretch distance, then you're going to do something very similar, except instead of making, let me make my little chart. Compression, speed, height, compression, speed, height. Instead of making, giving this all of the energy, we're going to give the compression or the stretch all of the energy. We're going to say there's no kinetic energy, no gravitational potential energy, and all of the energy that the system starts with will have turned into elastic. Now, there was never any potential energy gravitational because there was no height. So the equation then becomes 1/2 kx initial squared plus 1/2 mv initial squared equals 1/2 kx initial maximum. I know that's the maximum because there's no other energy. All of the system's energy has been turned into elastic, maximizing the stretch distance. So again, I divide both sides by 1/2 or multiply both sides by 2. Divide both sides by k, cancels that out, and it puts a k down here. And then I square root both sides. Oops, whoa. I square root both sides to get rid of the squared. And the final expression is maximum displacement is equal to xo squared plus mvo squared over k, all square rooted. That's it. Let's move on. 16. So now we'll take a look at 16. This is a wonderfully complicated problem, and there will be multiple ways to do it. So I will show you one way, kind of the first, really it's just the first one that comes to my mind. And maybe there's, maybe this is one you're less inclined to see because of the angles involved. So I'll show you this thinking it might have some value, but my challenge to you is find a simpler way to solve. We've got a 55 kilogram skier who starts from rest at the top of a ski jump, that's right here, travels down the ramp, which is frictionless, no air resistance. We have to first find her speed VB when she gets to the end of this jump. Now here she's moving horizontally, they say, because it's a horizontal ramp. At this point, the end is horizontal. We have to find also the distance s to where she strikes the ground. Now, this is not just a simple projectile motion problem because there's this extra vertical distance to account for. Okay. Here is the way I would recommend solving the problem, right? First, it's pretty straightforward to see that this is, if we make this the initial moment and we make this the final moment, then we can do energy conservation, speed, height, compression. Clearly there's no compression because nothing is stretched or compressed. Initially she does have a height, but they say she starts from rest. At the end she has, I'm going to say she has no height and just speed. So that means that I am treating as my 0 level, I'm making this my 0 level, such that she has height initial. The amount of height initial that she has is 45 minus 4.4. Right? Because from here to here is 45, from here to here is 4.4, so I got to take away the 4.4. And this is going to be an initial height of 40.6. So she's converting her height into speed, or more properly, she's converting her gravitational potential energy into kinetic energy. Let's do that calculation. mgh initial equals 1/2 mvf squared. The mass cancels, divide both sides by m. 9.81 times 45 minus 4.4 is equal to 1/2 of Vf squared. And maybe I'll call that V at location B. So I'd multiply both sides by 2, square root both sides, and what do we get? 28.2236. I'll do 28 meters per second for sig figs. But if I use this value again, I'm going to include all the decimal places. So here's how I like to think about the second part, which really I believe is the harder question. Determine the distance s along the 30-degree incline, right, 30 degrees, the distance to the point where she lands. So here's what I want to do. Here's my inclination. Inclination? Okay, here's the first thing that pops into my head. There will be other ways. Find a simpler solution. My first inclination is to say the horizontal distance she travels in the air is just her horizontal velocity multiplied by the time, right? The x-axis displacement in free fall, the x-axis displacement is just x velocity times time. Why am I putting distance right here? Because there's distance, s, on the hypotenuse. So this better be, this adjacent leg better be distance, because that's what the hypotenuse is. All right, so I've got her x distance, which back in unit 2 we talked about as delta x. Now I just need delta y, which is not from here all the way to the ground, but just from the bottom 4.4, the 4.4 ends down to where she lands. So that delta y, you'll remember an equation that says delta y is vi yt plus 1/2 at squared. And she's going down, so we expect this to be negative. If she launches horizontally, then the initial y velocity is 0. So now her horizontal distance downward or the displacement downward on the y-axis, is just half of her acceleration, which is negative 9.81. That's equal to negative g times t squared. But this hypotenuse is distance, not displacement, so we don't care about the negative. We just want the y-axis distance. And so let me drop that negative sign. So this leg of the triangle is 1/2 gt squared, where g is 9.81. Well, let's see. Put this together with this. How do you do that? Tan of 30 is half of gt squared over v times t. One of the t's cancels, and look at what we have. Let me just clear this off. If you multiply both sides by, if you isolate t, you get 2vb tan 30 over g is the time she's in the air. So we could calculate how long she's in the air, right? 2 times the speed from before times tan 30. Mode is degrees because we're putting in 30 degrees over, 9.81. 3.322 is the time she is in the air. So, okay, what's the hypotenuse S then? Well, we know the time is this. We know what VB is. That was the 28. So take that time and multiply by the 28.2236, ... And here is the x-axis leg of that triangle. Okay. So how do you get the hypotenuse? You know the adjacent leg. You know that you're looking for hypotenuse. Adjacent hypotenuse, that is cosine. Is adjacent leg over hypotenuse. Bring us to the other side and divide by cos 30. And we get this. 108 meters. And with 2 sig figs, it's about 110. Wow, that's a hard problem. You can use projectile motion equations. Well, we did kind of. Yeah, we did. But there would be other ways to solve. That's just, I've given you sort of maybe a different, unique way that you wouldn't have normally seen. 24, last one. A 3 kilogram ball is dropped from rest from a height of 2 meters. When it strikes the ground, 12 joules of its energy is lost to heat due to internal friction. So here's what's happening, and maybe not internal friction, but the idea is the ball is headed toward the ground. Here it is in the very last moment of free fall, right before it strikes. It hits the ground. Whoops. It hits the ground, and what happens? Well, it's a bouncy ball. Bouncy balls squish slightly. They deform. And I'm exaggerating this, but they stop briefly. And then they pop back up. Here it is headed down, and here it is in the first moment where it re-enters free fall. Here it is in between. And in this moment, because you're squishing the ball, the molecules start moving around. And so that random motion of the molecules is kind of heat energy. We call it internal energy. But there's energy, tied up in that motion. So if you start with, I don't know, let's make up a value. If you start with 22 joules and you lose 12 joules, that random heat energy or random internal energy of the molecules, then now you would have only 10 joules left, and so you don't go as high when you return back up. That's the scenario that's occurring. Now here's the thing. We're starting with gravitational potential energy here, because all we have is height. We're dropped from rest. We're ending with gravitational potential energy here, right, where we have some final height and mgh final. And if you apply the equation, mgh final, mgh initial, if you apply the equation for energy conservation, you can say the initial energy less the work by friction is equal to the final mechanical energy. And initially, all you have is mgh, gravitational. Oops. We know friction does 12 joules of negative work. I probably should make this plus work by friction because that's a negative value. You plug in and the negative is introduced when you plug in. But the final energy is mgh as well. So, okay, what's mass? 3. Initial height was 2 meters. And so you can simply calculate your final height. 3 times 6 minus 12. And then I have to divide by this to get rid of, to isolate h. 5.59. That's curious. I think that's a typo. I think it's supposed to be 5.59. Did I mess up? Looks like it. This looks like an error. 3 times 9.81 times 6. Oh, it's not 6. mgh. The initial height is 2. Let's try again. And then we divide by 3 and 9.81. Oops. Second entry. Oh, it is 1.59. And that's how you solve. Wow. 45 minutes of great physics. Nice work.